Good afternoon to everybody. Maybe some of you may remember that I took some lessons, two as last concerning automated metros and urban cableways. And now we complete the transport system, the sustainable transport system for urban applications with assisted tramways. And in particular, I would like to follow these four main steps. First, a very short historical evolution on tramways. Then, as typically in the transport domain, their hourly capacity, then the characteristics of the system, the infrastructure, the rolling stock, and the operation of trams. And last but not least, the recent innovations, the latest developments, and with a particular focus on the energy consumption of trams. So the goal is resumed here, the purpose, historical overview and future-oriented perspectives, then an overview on tramways, starting from the characteristics of the track and the infrastructure, then the rolling stock and the innovation, the hourly capacity, as I said before, and some developments. So let's start with the capacity, and then I will take a look at the historical aspects, going back to the capacity afterwards. As you can see here, this is a slide that I already shown with the seminar concerning automated metros. Typically, the tramways are of some kilometers of extension, and to obtain the hourly capacity, it's very simple, as you most surely or most probably know. You have the capacity of a single tram that is typically within 150, 200, 250, or a bit more passengers. Then you know the frequency or the time between two vehicles, and then you multiply the capacity by 3,600 and you divide it by the interval in seconds and you obtain the value of the hourly capacity. That is typically between 1,000, 2,000, could be a bit more. Sometimes you overlap services and it seems from a point to another point, maybe in the city, in the center of the city, that you have 3,000, 4,000, 5,000 passengers per hour per direction of capacity, but that's apparent because the single line can arrive around 1,000, 2,000, 2,500 or a bit more. Given that, if you want to increase that hourly capacity, you can go in the direction of urban cableways that you have already seen, or above 8,000-9,000 passengers per hour per direction, automated metros. So more or less, you can cover in the fixed ways the typical hourly capacity of a great number of European cities. As regards the history, the first trams were already in operation in the last 20, 30 years of 2 centuries ago. And why? This is an example, sorry, I will make a number of examples coming from the city where I live, that is Turin, and because there is a history and also an evolution. Well, within this history, what I want to underline, why did tramways why were they introduced? Well, because the roads were not, let's say, smooth. They were not planned. They had different irregularities. And the proposal was to place some rails to have a more regular travel, to reduce the frictions. And this could help horses which had to pull the trams to reduce their efforts. And this brought in those years to the development of some urban networks. This is the one in Turin. So a network in 1890s already operated with horse tramways or tramways pulled by horses. And then afterwards, and we speak about the end of the 2 centuries ago, the electrification started. And having some rails could help because you could place the electric line and with a pantograph collect the electric current. So the comfort, the reduced rolling resistance, and then the base for the electrification was the base for the development of urban tramways. But many years, some decades have passed, and nowadays we speak of both, let's say, traditional conventional tramways and fast tramways, where the typical feature of fast tramways are the segregated lanes and, as far as possible, traffic light priority. Given that there is a number of technical standards, I mean, mainly referred to CEN, you know CEN, European Committee of Standardization or Normalization, Comité Européen de Normalisation, which partially have the same rules or same technical features of railways, but typically standards, technical standards concerning tramways are for tramways, and that's all. They concern low floor, electric traction, the resistance of the vehicle. We will see them soon. So I've resumed so that if you have to deal with tramways, you know which are the bases in technical terms. So I've resumed all the European standards which concern tramways. Some of them, as I said before, come from railway application, but with a specification for trams. So I will not list them all, but I'll just let you know that there is a standard concerning tram vehicle layout, then displays, controls, indicators for tram vehicles, vehicle and, sorry, there is an error, and design for trams and light rail vehicles. Then something related to the mechanical requirements for joints, the performance requirements for rail fastening, the windscreens, interiors, special purpose rail within which there are grooved rails for the tramways. And then there are some technical standards concerning switches and crossing, urban rail application of railways, also for the tram train applications, of which I will tell you something later. Then a communication device for urban rail, the track during the work, and last but not least, MaaS, Mobility as a Service, which has a standard NetEx, which includes also the network and timetable exchange for trams, for knowing that is what is the supply of services of tramways together with all the other urban services. So this is the list of technical standards concerning tramways. There is a consolidated literature and consolidated standards. Given that, let's see, first of all, which are the main strengths of trams. Then we will enter into more technical aspects. The strengths are, well, the hourly capacity is interesting. 1,000, 2,000, 3,000 passengers per hour per direction, as I said before. And it's much more, let's say, attractive than conventional buses. And if you have a segregated lane, this guarantees, well, to a certain extent, that you can maintain that hourly capacity without the influence of traffic flows. Then, of course, the regularity of the lane, I mean, having some rails at disposal, guarantees the passengers to carry on some other activities like reading, like using their smartphones or whatever, while traveling. Then the frequency, if you have enough drivers and you have a good network, then you can guarantee a regular frequency of the service. That is something interesting. Then you typically, well, cities typically aim at protected or mixed-use reserved right-of-way, so segregated lanes. It doesn't produce, of course, local emissions because all the tramways nowadays, typically or nearly all, have an electric line. Well, there are some tramways with the rope traction, as you may remember from San Francisco, or some specific application, but typically they are all electrified with an electric line and a pantograph. And then typically an easy accessibility and a creation of a positive network effect, because you can have switches and you can cover parts of a city. Then you might have an effective traffic light priority, of which I will speak later, and this guarantees a higher, typically commercial speed. Then you can integrate the tramways with the urban context, especially in the central areas, as we will see later. And typically you have segregated lanes as far as you can with a clearly visible route, therefore less risky for pedestrians. It's not always like that, but could be. And then you have the possibility of recovering energy during braking, though it's not so easy for tramways as for trains. We spoke about that when dealing with automated metros. And anyway, you could do it and part of the energy will not be lost. Given that, let's start from the infrastructure. Maybe you remember that the typical standard gauge of railways is 1435. That is the normal gauge that was inherited from Stevenson at the beginning of 2 centuries ago. But the tramways have not the same railway gauge. It's a bit wider, just 10 millimeters, 1445, 1445 millimeters. And typically, as you can see here with the blue line, they have a shape so to guarantee that the vehicle stays there, notwithstanding the, let's say, little ready that typically a tramway can have in a city. Okay? And typically we have Vignol and Phoenix infrastructures rails that we will see shortly. As regards the running track, we have various gauges apart from the standard one that we have just seen before. So 1445, I go back, this one. Okay, apart from that, we might have the narrow gauge of 760 millimeters and pseudo standards. Typically, we can have very reduced radii. Consider that in railways, typically the radius of a railway line has a minimum of 150 meters, but this is not typically accepted along the infrastructure. And normally we have railways with more than 250, 300, 350 meters of radius. In the tramways, you can reduce that, given also the kind of infrastructure you have at disposal. Then you can have a gauge widening on curves, typically on very narrow curves. Then you avail yourself, the line can avail of switch point, and you can activate track switches from on board, typically of the vehicle. The rails are Vignol or Phoenix, and we will see later, typically grooved. And there are solutions for reducing the vibration, typically wooden sleepers or synthetic elements for absorbing vibrations. Here, sorry, there are some slides that are in Italian because I use them in my courses, but though some of them are in English, but these are in Italian. These are typically Vignol rail. What I underline is that you have, as you may distinguish underneath the rail, an element for absorbing the vibrations or in between the rails, as you can see here. As regards this application is very similar to the railway one. Then as regards typical tramways application, we have Phoenix rails like this, and they are much applied in many cities. And as I said before, they are very good for very narrow curves because the rail, the body of the tram remains there, cannot get outside unless for very, let's say, unexpected conditions of dynamics. As regards the layout of the track, here I have reported some few designs and some few sections of possible lines in the city. Well, you can see you can have either the tramways one close to the other with the electrification on the extreme parts of the carriageway or close to them in between. Or you can have the carriageway where you have the tramways in one direction and the other at the extremes and the lanes for the cars or passengers in between. Or you can have in the between, but in a specific context, typically where you have passengers apart, like in the picture below. So you have, let's say, parking areas or areas where people typically may walk, and you have the tramways in between. As regards the rolling stock, in the world, conventionally, we have three types of trams with 2 bogies, 3 bogies, and 4 bogies. Only recently we have longer trams that we will see later, up to 6 bogies, but the conventional ones typically are these. So a little tram typically has 2 bogies, like the one on the top left of this slide. Or you can have a 3 bogies tram like in the bottom part, or 4 like in the real bottom part of this slide. Typically, as regards the power supply, it has something like either 500 or 750 volts of direct current. The maximum speed by normal rules standard are typically 70 kilometers per hour. And we have not in the tramways the same resistance of trains. So one problem of the tram train solutions is that if you allow trains on a line, provided that you guarantee the distance of the rail, so the standard gauge in the rail, provided that you cannot allow the coexistence of a train or a tram, because the tram would lose in case of collision, because the resistance is much lower than that of a train. Then the train in some countries have 2 drivers, while the tram typically has 1. Okay. As regards the breakage or the braking of the tram, typically you don't just have the aerostatic braking and the conventional mechanical braking beside the electrical one that we have seen for the metros, but we have also electromagnetic pads. That means that you can press some pads on the rails in order to obtain a sudden and very rapid braking. This is not typically applied on trains, apart from high-speed trains where we have electromagnetic pads, because in case of emergency, the high-speed train has to reduce the speed in a very, let's say, reduced space, and this can be, let's say, veiled by the electromagnetic pads. But tramways normally have them. Okay, because they work in the cities, they operate in the city. Here you have a section of line, you can distinguish the pantograph, the section, the front and rear of the tram. Let's see some pictures, and then we will go towards the technologies. As regards the pictures, well, here you can see 3 bogies or carriage tram, the front, the side, and the plant views. Forget the number here, is just an application concerning Turin and some other Italian cities. So you can distinguish that typically you have 2 pieces which are connected together in the intermediate part, and the bogies that you can see there. Then the number of the doors depend on the kind of design. Here you have 3 bogies or tram or carriage tram. Again, you can see a similar concept. And another one. And this is instead a 4 bogies tram that normally are the longest one, apart from some very recent experiences that we will see shortly. And well, in a tram like that, you can host something like 250, 270, even nearly 3,000 passengers. Okay, so you can calculate easily the capacity given the time or the headway between 2 trams. More recently, so the first electric tram in the experience that I shown before, that is Turin, was introduced in 1899. Then there is more than 1 century, and nowadays we have trams like this. I've taken as an example a German one of 2024. That is, let's say, a very interesting tram with 312 passengers, 92 of whom are seated. Then the axles are motorized. So this allows for the overcoming of major climbs. Then here you have 16 asynchronous motors with a total power of 880 kilowatt. I don't know how much confidence you are with powers, but typically this is the power of, for example, a locomotive that you can use for the marshalling yards in the railway field. So comparing Here we have a tram which can arrive, in this case, more than 70 kilometers per hour of maximum speed. It arrives at 80, and in interesting power. Well, this solution is one of the longest in the world and can negotiate curves of 15 meters. That is something interesting because typically in the cities you might have to turn with so short curves. And it's bi-directional. That means that you don't have to invert on switches, but the driver can just change his position and you can invert the motion of these trams. Okay, some other features is that it allows, as I said before, energy recovery. But in this case, it's not given back to the line, as we say, as I said, and as we saw for the automated metro. Just recall that in the automated metro, typically having an electric motor, you can recover energy and give it back to the line so that another convoy can use that electricity for accelerating. And this is something very interesting. In this case, you don't give the electricity back to the line, but you recover with high-performance capacitors on board so that you recover that energy in the capacitor, like in a battery, and you can use it again for subsequent acceleration phases. This is what is made nowadays in cars with the hybridization, where you have the electric motor, the internal combustion engine, you have a battery, and so when you reduce the speed you use typically the electric motor, you recover energy for storing it in the battery, and this is similar to some extent. Then, this vehicle can travel without electrification for up to 1.5 kilometers without contact line. Okay, thanks to these batteries. And so this is an example. I took one of the few in the world that is very, let's say, up-to-date and modern. We are not speaking yet about technologies for the driver and energy, but again, anyway, as regards the mechanical and electrical parts, so this is something interesting. It has also some floating bogies, so that it allows for, let's say, very, let's say, critical curves in cities. Just to recall about one aspect that maybe you know from other seminars or from your experience, certainly, that is the instability during the rush hours. A very practical example. If you go to the bus stop or the tram stop, it can happen that you wait for a long time and buses don't arrive, trams don't arrive, then a bus arrives and soon after another one or other two, and the same for trams. The same can happen also for conventional metros. Why? Because of this. Because if you increase the time at the stop, I mentioned that already for conventional metros when I made that seminar. If you increase the time at the stop, then this means that at the subsequent stop you will have more passengers typically if they have a certain distribution in time, and this will increase the stop at the subsequent stop, and so on. This will make, let's say, the delay wider and will accumulate vehicles. Well, why do I recall this aspect? Because if you have a segregated lane and if you have technologies that you can nowadays apply on tramways, you can recover this at least to a certain extent, though the full recovery can be made with fully automated systems. But anyways, to some extent you can do that. And let's see, so let's go towards the innovation. Well, some innovation are related to the fact that the tram trains rules have been introduced in some countries, like in Germany, like in Italy, like in France. And this implies, of course, to have a train which has some features which are more similar to a tram, just one driver, the resistance that is lower to that than that of the train, as I said before, and can travel along an urban line. But if you have a lane, I mean, an infrastructure where you can allow trams with the appropriate gauge, of course, and electrification, well, typically in the tram train solutions, we share we separate the timetable of the trains and that of the trams. Otherwise, you have some rolling stock that is suitable for both lanes. Then most recent tramways have modularity of vehicles so that you can make them longer or shorter according to the needs. And a typical application related to the use of intelligent transport system is like traffic light priority. Traffic light priority means that you can localize the tram and you have under control with a supervisor the traffic lights. And according to the position of the trams, you can provide a longer green wave or green phase for the tram when it is close to the intersection, so to guarantee the green. And of course, in the subsequent phase, you will give back that extended green to the other flows so that you cannot, you will try to avoid accumulation of queues. Okay, given that, I've taken this picture, I've used this picture to show you that as an example, if you have the traffic light priority, the example is referred to Turin. I tested myself with my watch and I saw you count the number of traffic lights along a certain origin destination path, and you can obtain something like 80%, even more, of green phases, given the traffic light priorities, but at the condition that you have a segregated lane. This means that you can arrive to commercial speed. I'm sure you know what is a commercial speed, from origin to destination, including the stops and possible delays along the line, but from origin destination divided the time divided by the space, and space divided by the time for the speed, and you obtain a speed like 20 kilometers per hour. That is a very interesting one, commercial speed, in a city. Okay, so let's take some examples to let you understand what can be done with tramways nowadays. Here there is a survey made again in Turin, you have different drivers, so the different curves that you can see. And on the x-axis the time, on the y-axis the speed. So you can see how different drivers with different experience may have a different speed along a line. But given that, if you have a supervisor, and this is an example of a part of the supervisor in Turin, you can know what is the position of the trams, especially, preferably or much preferably if you have them in a segregated lane, because they are not disturbed by normal private traffic. And then you can guarantee the green light according to their position when they approach the intersection. Of course, it depends also on the position of the tram stops, because it could be far away from the traffic light or close to it, so you have to consider that too. Typically, you can give some more green light to the other flows, not in that of the tram, and provide an extended green phase to the traffic, to the tram along its traffic flow, and then, as I said before, give back this extension afterwards. So what can we do with that? We can obtain some numbers. I've just reported some experiences here. According to the different section, you can analyze what is the energy consumption. You can analyze what is the effect of the traffic light priority. And if you use these numbers, you can see that having at disposal the green phase for the tram, you can guarantee a reduction, of course, in the energy consumption that is not so irrelevant. Why? Because the great part of the energy consumption is associated to the acceleration phase of the tram, of course. Then once the travel is, let's say, at a certain speed, the energy consumption of a tram is very low, because you have this steel-on-steel contact, which doesn't imply a great resistance. That was one of the origin of tramways. And so if you don't accelerate, decelerate, accelerate, and decelerate frequently because of stops, because of traffic lights, well, this provides a great result or a sensible result in terms of reduction of energy consumption. What about, well, so we have seen the types of tramways, of infrastructures, of rolling stock, or barges, the most modern tramways. We have seen the effects, especially in terms of time, of travel time, so then commercial speed and energy consumption of modern tramways. But we have still one part to face, that is onboard technology. The driver can be assisted or not. So far, tramways have not been much considered in this context. Metros have been, with automated metros. Trams typically have a driver. But in the recent years, as you may remember from the seminar on automated metros, in recent years, the GOA, you may remember the grades of automation. In an automated metro, you have GOA 4. Well, GOA 1 has appeared in tramways. And you still have a driver, but the driver is nowadays, or can be nowadays, assisted. Some tramways in the world now have this GOA 1 application. And here I have reported this picture from literature on current and future system usage and improvement concerning automation on board. You see that we are at GOA 1, but we are addressing GOA 2, GOA 3, and GOA 4. It's difficult to reach a GOA 4 in a tramways because you cannot segregate it at all, since typically it operates in the urban context. But anyway, step by step, a higher level of GOA is under application. As you can see, the ATO, of which we spoke about in the metros, and HES, that is anti-collision system, then the CCS, that is crash call system, are typically applications on which there are researches and applications, first applications nowadays. Okay? There are also some applications concerning the insertion on board of radars and of leaders, so laser radars, and anti-collision systems, so to help the driver in case of he doesn't see or a sudden obstacle appears along the lane, along the rail lane, and this helps in terms of safety of the travel. These are very frontier applications of which some tests are undergoing. Well, this seminar is a bit, let's say, shorter than the previous ones because I wanted to make, let's say, very vertical analysis on the recent application of tramways and leave some more time for the discussion. And what I can conclude for the time being is that tramways are still alive and kicking, notwithstanding they have more than 160 years of history. And notwithstanding the fact that they were born for reducing the resistance with the rails for the horses, these rails still remain, and they have a role in terms of comfort. That was one of the reasons, but now it becomes important. And they have a role because they allow for segregated lanes, and tramways are still interesting. Of course, they have some thresholds that are typically related to their hourly capacity, because you cannot arrive to more than the numbers that you can see here, 3,000 passengers per hour per direction. Just to make an example, well, it's very simple. I take my smartphone. You can write, for example, 250. You divide it by, let's suppose, 120. Sorry. Bit more. You can have a tram, for example, each 300. No, 120 is too short. 300 that means 5 minutes, seconds, multiplied by 3,600. Okay, that's the maximum. That means that makes 3,000. What does this mean? That if you have a very, let's say, crowded tram, modern, with 4 bogies, and you can have a driver each 5 minutes, this is the maximum capacity, that is 3,000, that I've written in the slide you can reach. Sometimes there are advertisements. Here you have 5,000 passengers per hour per direction with these tramways. Not believable unless, as I said before, you might have some lanes that are overlapping. So one origin and a destination, another origin and another destination, but in the middle part of the city, they're overlapping. And so you can reach higher values than this. If you need anyway more capacity, hourly capacity, of course, you can address urban ropeways and automated metros. Then segregated lanes are something much important. They were not so pursued in the 70s, 80s, and 90s, but from those years on, many cities have reduced the capacity for private traffic and increased that for tramways, allowing for segregated lanes with traffic light priority. But traffic light priority is not immediate. There are both local, let's say, instruments. That means that the trams asks for the traffic light priority. This is typically, let's say, applicable for low levels of traffic. But when you have a city, an important city, this is not feasible. And normally you have a supervisor. For example, the one in Turin is called Utopia. The supervisor with inductive loops and with the localization of public transport knows the traffic flows and know where the trams are, also the buses, of course, and according to that, as I said before, applies strategies for reducing the levels of traffic in the city, and when the trams arrive, gives priority to that. Okay. Another evolution is that of Goa, as I said before. That means the grade of automation that nowadays is just at 1 and is evolving towards level 2, possibly 3 one day. As regards the energy consumption, the segregated lanes and traffic light priority have a great effect, as I've very, let's say, synthetically explained before. And this is important because the high attention that we have nowadays towards the energy consumption, the emissions that we have not, apart from, let's say, some particulate matter, but very little from tramways. Well, the energy consumption is very interesting because it's a typical energy consumption of a train, but lower and a bit higher than that of cableways, of which I spoke in a previous seminar. That's all. And there are some minutes for questions. A bit, I've been shorter than previous times, but I'm available for answering to your questions.